I would like to thank the organizers to give me this opportunity to present my work. This is Lijun Zhang from Shandong University of Science Technology, China. The title of my talk is Traveling Wave and Multi-Wave Solutions of a Class of High-Order Nonlinear Wave Equation. Here is the outline of the presentation. Traveling wave solutions are some special kinds of solutions to nonlinear wave equations. They can be usually characterized as solutions invariant with respect to translation in space. They used to describe the process of transmission. Solid wave is a particular type of traveling wave, which was first discovered by John Scott Russell in 1834. He was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses. When the boat suddenly stopped, the mass of water in front of the boat in the channel didn't stop. It formed the shape of a round, smooth, and well-defined heap of water moved along the channel, apparently without change of the form or reduction of speed. He followed on horseback after a chase of 1 or 2 miles. He lost it in the wind of channels. This singular and beautiful phenomenon was named as solitary now. Unfortunately, his great discovery didn't attract enough attention that it deserved, since no one could understand why this phenomenon could happen. The earliest mathematical model of wave on shallow water wave is the KdV equation. KdV equation was proposed in 1895 by a Dutch mathematician, Korteweg, and his student De Vries. For this equation, the exact solid wave solutions can be derived like this. They believe that these strange waves that Russell observed are caused by a cancellation of nonlinear and dispersive effects in the medium. Later on, a lot of model equations are proposed to describe the shallow water wave. For instance, Kamath-Helm equation, Burke's equation, and so on. A number of researchers have been working in this field, and some effective methods are proposed. Here I will introduce the dynamical system method. There are mainly 3 kinds of bounded traveling wave solutions: solitary, kink or anti-kink periodic wave, which physicists pay more attention to. They correspond to 3 types of the orbits of ODEs: homoclinic, heteroclinic, and periodic, respectively. So from this relationship, we know if we want to find the bounded traveling wave solutions, we only need to find the bounded orbits of the corresponding ordinary differential equations. Here are some pioneer works. Professor Jibing Li published the book in 2013, Singular Traveling Wave Solutions, Bifurcation and Exact Solutions, to present related work systematically. For a nonlinear wave equations, which could be reduced to a second-order ODEs, the corresponding planar dynamical system can be given by equation 1. Then, we will study this equation in different cases. First, let's say the case when g is a continuous function. A simpler subcase is that it is an integrable system. Like g is a function of f of x, that means g only involves in x. The orbits of equation 1 are determined by its Hamiltonian. In 2002, we started a generalized PC equation and obtained the bifurcation and phase portrait, which are shown here. From this phase portrait, we can see clearly the bounded traveling wave solutions of CP equations. Like for the first case, we know there are three families of periodic orbits. So we know CP equations for this case will have three families of periodic traveling wave solutions. And for this harmonic orbit, we will know it corresponding to a shorter wave of peak form. And for this harmonic orbit, we will know it corresponding to a shorter wave with valley form. And in this case, for this hadronic orbit is corresponding to a kink wave, and for this one, it corresponding to an anti-kink. And this one we know there is one family of periodic wave solutions. If system 1 is a non-integrable system, like for the KdV-Burke's equation, the corresponding system is given like this. And the phase portrait can be these two forms. Here we can find that there are two bounded orbits which connect the sandal and the two foxes. They corresponding to two infinite oscillate waves. For this case, there is a hadronic orbit which corresponds to an anti-kink. For the second case, if G is not in C, for example, G is given like this. Like if a PDE, the corresponding traveling wave solutions is in this form, then the function G is not a continuous function. These equations are separated into two classes. One is if the denominator u doesn't involve y, and the second case is the function u involves y. Please refer to these literatures for further information. The dynamical system to study the traveling waves has its own advantage and challenge. Advantage of this is first we can study the properties and existence of the various traveling wave solutions. It can be recognized very easy from the orbits of their phase portraits. The singular traveling wave solutions of nonlinear partial differential equations with nonlinear dispersion can be studied by this method. The challenge of this method is sometimes it's not so easy to analyze the bounded orbits of the dynamical system, especially for non-integrable system, even for planar dynamical system, not mention the high-order dynamical system. Is it possible to be applied to study the multi-wave solutions of nonlinear partial differential equations? These are the challenge of the dynamical system method to study traveling wave solutions. To address this question, we started a general fifth order nonlinear wave equations. It gave like this. And for this equation, we say it's a general fifth order nonlinear wave equation because it includes a lot of famous nonlinear wave equations that is very important in physics. It includes like the KK equation, the Lux equation, CDG equation, and KdV SKR equation, etc. And for this equation, we can introduce the variable cases x minus ct. Then this PDE can be reduced to a fifth order ODE. But for this in ODE, it can be integrated once, and after one's integration, it can reduce to this general form. And here G is an arbitrary constant because we integrate once and we get an arbitrary constant. And I also want to point out that here it also involves an arbitrary constant. And this equation equivalent to four-dimensional systems. And for these four-dimensional systems, we know it's not easy to find the orbits. But here, we can use this method to find the invariant. So the main idea is find the possible invariant submanifold in lower dimensional space. Luckily for this kind of system, we can find if the coefficient of this equation 2 satisfies the conditions like D. Here we have D. D is less than or equal to 3 times a squared over 40. We will find that y equals y cos a shows equation 2 if it can show order nonlinear ODE 3. And here we know the relationship between the coefficient A1, A2, A0, A1, A2, A3, and the A, B, C, D, E, F, G here. The relationship is like this. Here we published this paper in 2015 in Mathematical Problem in Engineering. If you want to see more details, please refer to this paper. And also in Journal of Applied Analysis and Computations. So the bifurcation and exact solutions of the first order nonlinear ODEs, if we find the solutions, then we can get the traveling wave solutions. And the bifurcation and the exact solutions can be started in 2015. Thus, the traveling wave solutions of the KK equation, Lux equation, CDG, SK, these equations can be derived. And this idea, just like I mentioned, the main idea is find the possible invariant submanifold in lower dimensional space. And if we couldn't find all the solutions in high dimensional space, then we find the possible invariant submanifold in lower dimensional space. Here is the main idea. So the same idea might be applied to study the traveling wave solutions of nonlinear PDEs, which even can be high order than fifth order. Like the only condition is if this PDE can be reduced into this form, the ODE only involves u prime square, u double prime, and the order of even order. If in this form, so the same method, same idea maybe can be used for this kind of nonlinear wave equations. Next, I'm going to introduce how can we use this method or this idea to find the multi-wave solutions of KdV SKR equations. The KdV SKR equations given by this. Here it involves two parameters A and B. And for this equation, it can be written in a weak form. And for this equation, we introduce two variables, independent variables, C1 and C2. We introduce C1 is x minus C1t, C2 is x minus C2t, and we let u equals capital U C1 plus V C2. If we can find a suitable C1 and C2, C1, C2 we call it wave speed. If we can find C1, C2 and find the solutions in this form. We call it two-wave solutions because it has two speed, C1 and C2. After we introduce this U, capital U C1 and weak C2, then this equation can be reduced into this form. Now let us look at equation 6. You will find that each of the four brackets only involves U or V. Here, U, here involves V. We specially organize it in this form. Then we can see if each term inside the bracket is 0, then the sum will be 0. That is to say, if U and V satisfy equation 7, then they solve. Now let's say how can we solve the system 7. 7 are two systems, but the two systems are symmetry. If we change U to V and C1 to C2, F1 to F2, then we will know that the two systems are same. So if we can solve one system, then similarly we can find another one. Symmetry, if we can solve for U, then similarly we can solve for V. For the first system, we found that if the two constant f1 and f2, if it satisfies this equation, that is, if we choose f1 and f2 like this, u c1 satisfies the first equation. This is a second order differential equation. Then it shows the second equation. That is, it shows the whole system. So we use this property, then we can solve this system 7. And we get this theorem. It is U C1 and U C2 and V C2 satisfy equation 9 and 10 respectively. Then U capital U plus capital V solves the KdV SKR equation. This is the main theorem. We know equation 9 is a first order nonlinear differential equations. By the bifurcation analysis, then we can find all the solutions of equation 9. Similarly, we can find the solution of equation 10. The equation 9, we find the exact solutions U1, U2, U3, 4, 5, and 6. Similarly, we can find V. We can find V1 to V6. After we get the solution U and V, then we have the theorem on the exact solution of KdV SKR equation. That is, this KdV SKR equation admits the traveling wave solutions Uij. It's a sum of U capital Ui plus Vg. Here Ui and Vi are determined by the solutions, the formulas we just presented. And C1, C2, that is the wave speed, satisfy two conditions. We use the numerical simulations to plot the graph of these exact solutions. We get there are three kinds of solutions. The first one is U and V. If we choose U and V as solitary wave, we get the solution is like this. The second graph, we choose U and V are periodic wave. And the third one, if we choose one is solitary solution and another is periodic, then we get the solutions of this. So by this method, we get plenty of traveling wave solutions. Here are the two-dimensional portraits of the two waves constituting of two solitary waves. We can observe the interaction of the two solitary waves clearly from these portraits. And this one is the two-dimensional portraits of the solution constituting of two periodic waves. And this one is the portrait of the solution constituting of one solitary wave and one periodic wave. Let us make a conclusion of this talk. We can get bounded of traveling wave solutions, even multi-wave solution, to a class of high-order differential equation by using the lower dimensional invariant manifold and bifurcation analysis. I believe this method also can be applied to study other high-order nonlinear wave equations. Thank you so much for your attention. Please contact with me by email if you are interested in this topic. Thank you.